attending these sessions. So during this session, you may interrupt me if you have any questions, okay, anytime. If you do not understand something, you please ask me.
Yeah, I will read out the chat for you. I have purposely like muted them because otherwise anybody opens and forgets to close it. Okay. So participants, you please raise your hand. I will help you. Thank you.
Yes, and yeah, if later if you have any questions, then you please drop mails in this email address which is mentioned in the footer, partho@cs.iit.ac.in, and you can explore the work what we are doing in IIT Roorkee. So these are all mentioned in this website, parimol.iit.ac.in. So all the publications, projects, these all are detailed here in this website. Okay, so let's start. So I think in the last session you have covered this supervised learning, unsupervised learning. Okay, so what is the difference and how it's actually these are working? So as you know, as you see this computer vision and machine learning, these are mostly done with the deep neural network or deep learning. And neural network is the backbone of this deep learning. So if you want to know the details of deep learning, you have to understand the engineering of this neural network. So this session is very important for this course. So we are going to discuss, I will actually take two sessions. So in the first sessions, we will have this neural network and how this neural network is actually working, this backpropagation algorithms. And tomorrow I'll take the second session where we'll be discussing different tuning of this neural network, how we can improve on the system of neural network. So whatever you get the results using this simple artificial neural network, how we can improve on this neural network systems. What are the tuning parameters where we can change? And once you learn those, this will help you in deep neural network for understanding how to improve the full architecture or full system. So in today's sessions, we'll be covering this artificial neural network, and there will be two parts. So first part, I'll be covering the perceptron learning, and in the second part, I'll be taking this multi-layer perceptron. So in this artificial neural network today's sessions, so the first hour, I'll be talking about this perceptron with a single neuron, how it works. And in the second session, in the second hour, I'll be going through this multi-layer perceptron. Okay. So in perceptron learning, so we have, this is the agenda, that's simple classifier. First, we see that how we can develop a simple classifier when we have different features. Okay, so how we can develop a simple classifier which will provide us a separation of two classes, and then from that we'll move to this perceptron and some parameters of these perceptrons are weights and bias. What are these? How we can handle those stuffs? Okay, what are the geometrical representations? And next we'll go through a learning procedure of this perceptron learning, and we'll also see this working principle with some examples. Okay, so how it works with some examples, simple examples. Okay, so let's move with the simple data sets. I think you have already seen in supervised learning and supervised learning. So you have a, for example, supervised learning, and in supervised learning, you have some features. These are the features like x1 and x2. Okay, so these are independent variables. X1 feature is height and width is x2, and then we have this class level y. Okay, so let us consider that this informations, these are all normalized. Okay, with this by z-score normalizations, that means that this the mean is all 0. Okay, so and you have this these are normalized with this variance as well. Okay, so just now consider that we have these two independent variables x1 and x2, and we have this y. So for example, we have different objects, characters. Okay, so like 0, 1, 2 different characters, and I just find out what is the height and what is the width. Okay, so these are the informations. So you have, for example, several examples, 0, 1, 2, or several other examples are there. I'm just considering only two examples. Okay, so 0 and some other examples like 1. And now I'm just, so there are 4 examples. Let us consider this is 1, 2, 3, and 4 examples. And for each of the examples, I am having this height information and width information. What is the height and width? And this is the class level. Class level, it is like it is 0 and it is 1. So that means it is a class level 1 and class level 2. So there are 4 examples, 0.5, minus 0.35, and class level is C1. And then you have second example. So these are the second example's data, that height is 0.35, width is minus 0.3, and outcome is C1. That means up to 0. Let us consider. So similarly for second category, so you have this height and width information. So you have this 4 examples are given. Now a new example comes, which is a test example, and where you have this height and width, and I want to predict what will be the class level, whether it is C1 or C2. Okay, this is my this will be my predictions, whether it will be C1 or C2. If I want to visualize these informations, okay, so let us consider that if I am having lots of data, and as I am having only 2 features, so I'm just I want to visualize. Okay, so those 2 all this data in this 2 dimension, we have this x1 and x2. x1 is height. Okay, so let us consider that I am having several examples, 100 examples. So some of these examples are with 0, and these are all blue colors, and some of these examples are red. These are in red colors. Okay, so some examples are given. Now if I am having some test examples, okay, so something like this, that's minus 0.2 to minus 0.5, some examples are given. So I need to predict what is the class level. It is C1 or C2. Okay, that's the objective of this supervised classification. Okay, machine learning. So here we want to develop a simple classifier for doing this. How we can develop? So I want to know what is the class level of this example, because we do not know. This is the test example. Some test examples come. We want to know what is the class level. It is C1 or C2. That means whether it is a blue or red. So can I find something like a linear combination of these features so that it can provide me the classification? If I just pose this problem in this way, can we get some answer? Okay. So for example, if I'm having these features like x1 and x2, can I get an answer y? So it can be thought of like, for example, if I'm saying that I am having, for example, several fish. Okay, so fish is like salmon and sea bass. Okay, so let's consider this one example, salmon and sea bass, and some salmon fishes are very small and sea bass is larger, longer. So and then if I see that some examples are there and their length, some of the examples are, for example, if I say that salmon fishes are something here, okay, and the sea bass examples are something like this. Okay, so there are several examples, and then if I am having 8 examples or 9 examples, and then if this shows this length features, okay, of these fishes, and then I want to make a classifications of these examples through some simple features. Okay, so just I will say that, okay, so can I say that if the fish, any fish comes with the length feature, if it is greater than 10 unit, then I will say that this will be sea bass, otherwise it will be salmon. So that means if it is a length features, I am saying I am making a thresholds. Okay, so threshold is like this. Okay, so it is a threshold which is found, okay, somewhere, that okay, so it is the length is 10, and given any fish comes, and if the fish length is more than 10, I will say that it is sea bass. If the length comes less than 10, it will be salmon. Okay, so this way is also a simple automations, and then I can do it using it's a classification also. So given any fish comes, okay, any fish comes, I just find out the length. Okay, what is the length? And this length, I'll just say that whether it is more than 10 or less than 10. And then accordingly, I make the I make the prediction. Okay, so now if I am having this only one length, okay, so then I can do it. Now if I am having this, now I am having 2 features. Okay, so 2 features comes like height and width. Can we do something like this simple things, that if I combine these 2 features and it will provide me a thresholds, and based on which I can predict? Is it possible? So what I mean that, for example, if I am having these features like x1 and x2, like 0.5 and minus 0.35, and can I make some combinations like 0.5 plus minus 0.35? Okay, so x1 plus x2, and then whatever value we have, and then accordingly I'll make a thresholds. Okay, so if I just combine x1 plus x2, I'm just making a summation of these 2 features, and then whatever value comes, so then based on this, it is, let's consider that this is the x1 plus x2, and then I'm making a prediction according to the thresholds. So it is the length is in this x1 plus x2, and then whatever fish examples comes, I'm just adding this x1 plus x2, and then I make a thresholds, and then I will decide that whether it is the 0 or 1 here. Okay, so is it possible? Can we do it something like this? It can be a simple summation, or it could be some weighted summations. Like for example, if I say that, okay, maybe height is more important than width. So here what I did, I'm just taking a equal weightage. Okay, so height, means height is also same weightage, width is also same weightage. That means I'm considering half into 0.5 plus half into minus 0.5. Okay, and then I'm dividing by 2. Okay, so then I'm taking a equal weightage of both the features. So can I make some weightage of these features? Like I can say that W1 into x1, some weightage of W1, and then I can say that another weightage like W2 into x2, and then whatever information I have, and then I can make a thresholds. Is it also possible? Okay, so that's a simple linear combination. Okay, so I'm just combining these features. Okay, so with some weighted values, and then I take a thresholds to predict whether the class is C1 or C2. right? So I am having now two features here in this example, x1 and x2, and I want to make this weighted combinations and use a thresholds to find the predictions. Note that in these examples we are having x1 and x2. In some examples it can come x1, x2, x3. In some examples there can be 10 features. So all these features I can add with some weighted average, and then I'll make a thresholds and make the predictions. Okay. So let's see that how if you can do it. Okay, a weighted sum can be formed by x1 and x2, and then consider data like 0.5 and minus 0.35, and then if weights are considered, okay, so some weights we are considering, that's I was saying that I will take, for example, 75% of 0.5 and 25% of this value. So if I'm just taking these two values, so this weighted sum will be w1x1 plus w2x2, and then it will come as 0.75 into 0.5 plus 0.725 into minus 0.35, whatever it is, 0.2875. Okay, this is the total sum. So I am getting one number from these two features. Now from these two features I am having a number, and now I make a thresholds. Okay, so let's consider this threshold is 0.1. Okay, so here the threshold is, if I am having a 0.1 thresholds, and then that's actually like a step function, that if this total sum is more than 0.1, then it will be category 1, otherwise it is in category 2. So as my sum with this w1x1 and w2x2, okay, so if I just multiply, and w1 is 0.5 and w2 is 0.25, and if I'm getting a weighted sum, this comes as total 0.2875. And now I have placed one threshold function, that is u, that is 0.1. Okay, in my earlier example I have used this threshold as 10. Okay, so I need to also set up. Okay, so based on which actually I see that all my results are correct in the training examples. Let us consider that using this 0.1, my data are all classified properly. So then if you have this 0.2875, then if I just place that, okay, if this total value is more than 0.1, that means 0.2875 is more than 1, that means the class level will be 1. Okay, that means it will be y equal to c1. Okay, so similarly for any other examples, I will just do the same step. So if I'm just fixing this, w1 will be 0.75 and w2 is 0.25, so I will always use the same weights everywhere. I cannot change for some examples with the different weights and some other weights for some other examples. This weight should be fixed for all these examples in an application. So now if we have this weights 0.75 and 0.25, and now if I am having another examples, let's consider this as another example, and where the sum is minus 0.25. Okay, this total sum becomes minus 0.25, which is less than 0.1. Okay, if the sum comes as minus 0.25, okay, then it will be classified as C2, because we have mentioned that if the total sum is more than greater than 0.1, it will be class 1, otherwise it will be category 2. Okay, so like this we can classify all these examples once we know that what is the W1 and W2. So we have now this, as I said, that we have a threshold that is of minus 0.1. Okay, and then what we did, we have these two features, x1 and x2, and this is the class level target. And what we added, we used this w1 into this multiplication factor, this x1, and w2. Okay, this is the weightage of this x1 and weightage of this x2 features. And then what we did, we had a threshold. Okay, so that threshold we used for this predictions. Now when we use these thresholds, Okay, so that threshold actually once
can I?
Yes.
So there are a couple of questions. So एक तो ये है कि what determines weight?
Yes, I am going to discuss. I am going to discuss. Yeah, just
And another question is how threshold value is decided. So
yes, this will be discussed. This will be discussed. This I am just taking one example. Yes, I'll explain. I'll explain all this.
I know you are going to explain, but I thought let me tell you.
Yes. Just you just see that it's a simple classifier. I am designing. Okay, myself. Okay, so let's consider that it's a simple classifier we are designing to solve one problem. Okay, we are going to discuss all this. Okay, so we have this, what we discussed, that we have two features, x1 and x2, and then we are multiplying this x1 with w1, x2 with this w2, and then whatever value we have, this total sum, and then after that we are using a threshold to have the predictions. And threshold is decided that, for example, I have told you that it is more than 10 in some examples, and some examples here I have seen this is 0.1. So why we are doing it in different ways? So instead of that, instead of this 0.1, 0.2, or 10, I am just adding that number here in this total sum. Okay, so then what will happen? What is the advantage here? So this will come as this. If I say that w1 x1 plus w2 x2 greater than 0.1. If it is more than 0.1, then it is of one class. Okay, then what I'm saying that, okay, let us consider this equation in a different way. W1 x1 plus W2 x2 minus 0.1, then I'm just taking whether it is greater than 0 or not. Okay, so instead of this greater than of some numbers, I'm just taking that number, the threshold value, I'm just moving it into the left side. Okay, so now my equation actually becomes w1 x1 plus w2 x2 plus minus 0.1. Okay, that addition of this minus 1 value is weighted. Okay, so it was checked. Okay, so whether it is total value is more than 0.1 or not. Now what I am doing, I am just reducing that value minus 0.1 from this sum. Then I will check whether this total sum is greater than equal to 0 or not. To shift this total value and compare with the to shift the total value to the thresholds where the threshold is 0. So I'll be using a threshold as 0. So if the total sum is greater than equal to 0, then it's of one category. Otherwise, it is another category, second category. Okay, so now this question, it's because if you just say w1 x1 plus w2 x2 greater than minus 0.1 or not, instead of that, what I am doing, w1 x1 plus w2 x2 minus 0.1 greater than equal to 0 or not. Okay, so same thing what I am doing. So instead of this greater than equal to minus 1, I am just adding minus 0.1. Okay, so here it will be minus 0.1. So it is now whatever I have this x1 x2, so I am just multiplying w1 x1 plus w2 x2 minus b, and this total value, if it comes as greater than equal to 0, then it will be 1, otherwise it will be 0, one category. So here initially I had this value as minus 1. Now this minus 1 I am adding it in the total sum. So now this threshold becomes 0. So I am just adding these numbers with this total number and then check whether this total number is positive or not. Okay, with the simple calculation. So I am just having this total sum w1 x1 and plus w2 x2, and then I am checking that whether this and adding this b, this threshold, and see that whether this number comes positive or negative. If it is positive, then it is category 1, otherwise it's an C2. So if we see this, we have, for example, if we, for this example, 0.25 plus into W 0.75 and minus 0.35 into 0.25 minus 0.1. If this total sum comes 0.1875, it is positive, then I will say that is C1. So this calculation actually becomes simpler. Okay, and if this, for third example, if you have this W1x1 plus W2x2 minus 0.1, and if this total value is negative, it will be C2. Okay. So now this threshold, this step function becomes, it was initially with this at minus 0.1 level, okay, and now I am shifting it to the 0. So always the threshold will check at the 0 level. Whether it is positive, it will be in one class. If it is negative, it will be in other class. Okay. So with this simple introductions, okay, so that we have got the simple classifier, that whatever we have this features, we just multiply with some weights and then add some numbers. Okay, this number is called bias, and then whatever total we have, if the total is positive, greater than equal to 0, then it is of one category, otherwise it is other category, second category. Okay, now let us take one example here. I'll come, okay, so all your questions will be answered. So let us consider that you have a problem whether a credit card holder will be defaulter or not. Okay, so you have a data set. This data set, so you have these three attributes x1, x2, x3, and you have this outcome y. So this inputs, this independent features are married, yes or no, 1 or 0, own card, means he is owning a card or not, 1 or 0, and then he is having job or not. Okay, and then if you see that these are the different examples, and some examples are -1, some examples are 1. That means he is having some somewhere is a defaulter or not. Okay, so these are the some examples. Now from those data, can we train, can we make a model, and then we can, if we have some different data, different variations, then can we see that whether it will be correct or not. Okay, so you have these three different features, x1, x2, x3, and then we are having, what we are doing, these are combined. Okay, all this these are combined with some weight factor. Then let us consider this W1 equal to 0.23, W2 is equal to 0.3, W3 equal to 0.3. Okay, so x1 is multiplied with weightage of 0.3, x2 is 0.3, x3 is 0.3, and then we have t equal to 0.4, which means you are actually having this bias minus 0.4. So I'm just finding out this value, that 0.3x1 plus 0.3x2 plus 0.3x3. Okay, so 30% of this x1, whatever value I have, and 30% of x2, and 30% of x, whatever we have discussed. These are of weighted combinations, right? That I said W1x1, W2x2, W3x. Now take any value. Okay, so for example, this, if I'm just taking 1, 1, 1. So what will happen? 1, 1, 1, that means it will be 1 into 0.3, it will be 0.3, 0.3 plus 0.3. That means it becomes 0.9, and minus 0.4. It becomes 0.5. If this total value is positive, then it is 1. Okay, so you see that any example comes, you can actually solve this using this simple words. So let us consider another one data, this one. The 0, 1, 1, minus 1. Okay, so here 0 is x1 will be 0. Okay, 0.3 into 0, 0.3 into 1, that means 0.3 plus 0.3, that means it will be 0.3 plus 0.3, it will be 0.6. 0.6 minus 0.4, then it will be 0.2. Okay, so that is also correct, it is positive. Let us consider another one negative example here. x1 is 0.3 and this others are 0. So 0.3 plus 0, 0 minus 0.4. Then 0.3 minus 0.4 is minus 0.1. So that means it is negative. So your outcome is negative. So you see that with the simple combinations of weights with these features, so this is possible. So what are important? What are requirement here? Requirement, what we did here, we have two things. One is we are doing some weights. We are combining all these features with some weights. And then we are adding a bias. Okay, so all these features are multiplied with weights, and then finally these numbers, whatever sum we have, we subtract with a number that is called bias. If this total value is greater than equal to 0, it will be of one category, otherwise it's other. Okay, so that's our simple classifier. Now with this introduction, yes.
So I saw a couple of questions. Why
Madam,
we
please
need a bias?
let me cover a few more slides.
Okay,
I'll take it.
Sure.
So now with this introduction, so let us see this how neural networks actually work. So artificial neural networks is developed to mimic the processing of neurons in the human brain and are designed to recognize patterns. Okay, so in human we have lots of neurons. Okay, and then these neurons are actually whatever the working principles, okay, in these neurons we have. So we try to mimic that similar principles, okay, and then that's actually called artificial neural network. That's why this artificial comes. So if you see this figures, okay, so in biological neurons you have lots of neurons, okay, billions of neurons. In artificial neurons, neural network, we do not have this many neurons, but we have less, and these are all not so complex structured. Okay, there is structured patterns of these neurons. Okay, so here I'm saying that these are, for example, height H1 that I've said, H1, W1, or some other features, and these are connected with some neurons. Okay, these are all neurons, neuron 1, neuron 2. Okay, and there you have several neurons, and these features are connected to neurons, each neurons, and these neurons are also connected similar to your biological neuron, and finally we get the output layers. So it's actually this brain neuron. You have lots of neurons are there. So that I was saying, so for example, if I touch one hot vessel, okay, so immediately I will pull it out. So that means my brain actually giving me signals that, okay, so this is hot. So that signals are coming from the brain, and then it's actually saying that, okay, so you should take your hands out, okay, pull out, and then you otherwise it will be burnt. Okay, so something like this. So similarly, we are developing this according to the similar principles, this neural network, where we have several neurons are there which are connected one after another, and one neuron processes some information and it provides that information to the next neuron. Next neuron process something and it provides to the next. Okay, so they are actually distributing the works one after another, and finally this work or the sense is passed to the actual place. So we have now these are the similarities that in the biological neurons you have this neurons, and there are actually multiple neurons which are all connected, and in this neuron you have this dendrites and axons. So these impulses are carried to this cell body by these dendrites, and in the cell body they process those informations. So whatever we receive, those informations are processed in this cell, and after this processing, that information is passed to the next neuron by these axons. Okay, so that's actually in biological neuron, and in artificial neuron also similar things are happening. We are actually following the similar principles. We have some informations coming from this, let's consider the features. These are coming through some sensors, and these are all processed by a neuron, single neuron, with some calculations, computations, mathematical calculations, and this process the output to the next neuron. Okay, so same thing here. You have a neuron which actually receives some data from other neurons, and it processes, and then after this processing, whatever data it has, it actually sent to the next neuron. So similar to your biological neuron. In artificial neural network, we'll be learning first this simple basic perceptron. Okay, that I said that this part is first the perceptron learning, and then perceptron means it's a single neuron. Okay, single unit is called perceptron. First, we'll be learning how a single neuron works. Then once we now learn that how a single neuron works, then we'll be working for multiple neurons. That's actually multiple neural network. Okay, so in this single neural network, single neuron, so we have to see that how this neuron is working. Then what are the architecture, means how these are connected. You have seen this, there are several connections. Okay, so what are these connections and how this model is actually learning, how this perceptron is learning, and that what informations need to be processed and how. So this artificial neural network, you have this basic perceptron. First I will go through this perceptron. Simple single perceptron means a single neuron, how it works. So it has a single node or single unit where it is associated or it is connected to numerous features. So for example, x1, x2, x3, xn. So in our examples, I have considered height, width. You may consider also density, or you may consider, for example, some other features like number of the lightness, okay, illuminance, okay, so several other features, and those features are connected to in this perceptron, okay, with some weights. Okay, so each of these features are connected with some weights, and then this neuron or perceptron process all these weighted features, and then it sends to the next neuron. Okay, so weight determines the strength of that features, means how that feature is important, what is the importance of that feature, then accordingly this weight is modified. Okay, so in this perceptron we have seen that two things, one is weights and another is bias. Okay, so we are going to see this, how these weights and bias can be decided, how we can learn them, train them. Okay, so these things we need to learn. So we have seen this x1 into this weights are means how actually we are going to combine them. X means we are going to have a linear combination, x1 into w1, x2 into w2, x3 into w3, and then we are having some bias, okay, to pull the total value close to 0. Okay, so that means we will check whether this total value is positive or negative. That's why this bias term. Okay, so bias term is coming to pull this total sum either to the origin 0, if its total value is positive or negative. If this total value is positive, then we will say that it is category 1, otherwise it is 0. So here what we have done, w1 x1 plus w2 x2 plus w3 x3. So this can be simplified with a simple equation w transpose x. Okay, in vector calculations you can write that w and x. Okay, so w transpose x means all this actually, if you simplify, this comes as w1 x1 plus w2 x2. These are all dot products. Okay, means whatever w you have w1, so this will be multiplied with x. So if I'm just giving you examples like x1 is height, and just I'm multiplying x1 with w1, that's 30%. Okay, so that's actually this 30%, 0.3 into x1, 0.2 into x2 plus 0.5 into x2. That's it. If this total sum plus bias is greater than equal to 0, it is of one category, otherwise it is second category. This perceptron does only binary classification, that I have already been explaining, that whatever we are doing, there is a one threshold, either it is greater than equal to 0 or it is less than 0. So it will be a binary classification, not multi-classifications. We can use only perceptrons for two category classifications, not more than that. If we have the data in two-dimensional feature space, then it will be a line. It will this separator, we call it a line. So let us consider this one example here. I think I have one example. Just let me see. Yeah, you have, for example, you have this some data, positive data, some negative data. Okay, so this is a line. Okay, this is, for example, you have this y equal to w1x1 plus w2x2 plus c. Okay, so this is the equation of this line, and this line, it will say that if the values are more than greater than or equal to 0, then it will be of 1 plus, otherwise it is second category. Okay, this is the geometrical representation of this line. And now if we just relate, okay, this to the neuron, okay, so this will be coming as you have this input, you have this synapse, okay, W1, W2, W3, and then you have the cell body where these are actually processed, and then after that we have this functions which actually calculates using a function, and this produce the whatever output it produces, it's actually sent to the next neuron. Okay, so that's actually f function is what it is doing. F is here, it's a taking the data as w1 x1, all these summations plus b, and then it will be using a step function if it is positive or negative. Okay, if it is greater than or equal to 0 or less than 0, that's actually the function. So it's either a step function that it is saying that it is category A or B. So that's the similarity of this neuron to biological neuron. Yes, I can take the questions now. Yeah, madam. Yes.
Yeah. Sorry to disturb. I keep disturbing you. In fact, there are questions which were at that time. Some questions were popping up. So Robbie, sure. Some Robbie is asking why we need a bias, and a similar question is asked by Anjit. What is the purpose of bias?
Yes. Okay. Yes. Anything else, madam?
There is another question by Ilyas that what if we have more than 2 classes?
Yes.
So that, and then Sunil Kumar is asking how to calculate the weights. Yeah.
Okay. So calculate these weights we will be learning, okay, later. And then, okay, first let us see this, what is the bias? Okay, so that's actually, we have this next slide, what is bias? So bias can be considered as another weight. Okay, so you have, as I was saying, that if we do not have bias, then what will happen? Okay, just show me. Let me just a minute. If I slide.
And one more question: what is the need of adding non-linearity in the network?
Okay. So if whatever I have done, that for example, if this function line is y equal to w1 x1 plus w2 x2, okay, plus b, and that's b, I'm saying it's the bias. That means it's actually a threshold which is actually keeping me the total value is more towards 0 or not. If you see this w1 x1 plus w2 x2, it's actually a line. So for example, if I am having 2 features, x1 and x2, okay, so x1 is a feature, let's consider height, and x2 is a width. Okay, and let us consider this weight. It is like you have 0.5 here and it is 0.5. Okay, so w1 is 0.5 and w2 is 0.5. So if you have this equation y w1 x1 plus w2 x2, so through which actually, and this equation, then there's data, how I will separate? I will say that w1 x1 plus w2 x2 greater than or equal to 0 or less than or equal to 0, right? If I am saying this w1 x1 plus w2 x2 greater than or equal to 0, then you will see that this equation will be always passing through the origin. Okay, so if there is no, we cannot add any other values. Okay, so means this line is always, this separator is always through this origin. Means whatever points we have, whatever data we have, I have shown you these examples also. Yeah, if I am having these examples, so I will have this data, it's always be going through 0, 0. Okay, so the line will be either through 0 here in this line, any other lines. Okay, I cannot make this line beyond this origin. Okay, so I cannot make this line somewhere from this origin. Okay, so I cannot drift it from this origin. Okay, so this is the reason that we are adding this bias. If we do not have bias, always this separator y w1 y is w1 x1 plus w2 x2. Okay, so it will be always through this origin. Okay, this is one of the reasons. And then if you see this another that I have also shown you this example, that for example this fish examples come. Okay, so if you see in this real time examples, this fish examples come. So fish examples will be all are, for example, some are 5, 7, 8, 9, some examples. Okay, then what I am doing, I am making a threshold. Okay, so like if the total value length is greater than 10 or less than 10, then only I can decide that it is CBAS or Salmon. Okay, so that means we have a threshold. We are not saying that originally that always this threshold will be 0. If I'm saying that the value is always threshold, that means I cannot distinguish all these examples. Okay, so all these examples are positive only. If I'm saying this y is always greater than equal to 0, then there will be only one category. There will be no category, the second category, right? Do I have any second category? Because if I'm just saying that the length is, if the length is greater than equal to 0, all fish examples are greater than equal to 0. So I cannot decide anything. So I have to make some value, okay, like 10, 15, something, through which I will decide that whether these fishes are salmon or it is sea bass. Okay, so that value, what I am saying that 10, so that I have to consider. So that means what I am saying that whatever W1 X1 plus W2 X2 comes, and then I am adding. So for example, I am saying that it is total value is greater than equal to 10. Okay, so if this total value is greater than 10, then it will be salmon. Otherwise, it is sea bass. Right. So if this is the thresholds, okay, so let us consider now that instead of 10, it is B. Some W1 X1 plus W2 X2 greater than equal to B, then only it is a positive, then Y is 1, otherwise Y is 0. So this equation can be rewritten, okay, in this formula W1 X1 plus W2 X2 minus B greater than equal to 0. Simple. Okay, just B I have written in this left side. So this outcome means I am just comparing with this 0 only. So whatever I had, this total sum, I am just subtracting with this B, so that now this sum, whatever outcome, whether I am just taking whether it's positive or negative, then it is Y equal to 1, otherwise it is 0. Okay, same thing I am doing, right? Is it okay?
Yeah, so please, I hope they must, yes, thanks, clear, he has written clear.
Okay, great.
And Anjit has also written thanks.
Okay, so any other questions now? Okay, so now let us see this.
Just a minute, let me scroll down. Can we treat this as a normalization? One question. And can we say that bias is basically a y-intercept?
Yes, bias is a y-intercept only.
Can we treat this as a normalization?
Yes, bias is a y-intercept only. Yeah. That's it. Bias is a y-intercept. Okay, so whatever we have, that's actually bias is a y-intercept, and that we are considering to take this this thresholds. Okay, so that if we just have this total sum, it will be greater than equal to either positive or negative. Okay, so if we see
and
this visualization,
in case of multi-classification, how to set the bias?
Okay, so that's we are going to see. Okay, so in this perceptron, you cannot do with this multi-class classifications. Okay, so we will be taking it into multi-layer perceptrons. Okay, there we can discuss. In this perceptron, there is no multi-class classifications. It will be only binary classifications.
Yeah, that's all.
Okay, and if we want to go for multi-class classifications, then we cannot do it a single perceptron. There can be a way. Okay, so let me also answer. We can have, for example, you have these 4 features x1, x2, x3, x4. Okay, so then we'll have one perceptron that will give you the answer. Like, for example, it is for example, this we have 3 examples. Okay, class levels. Like one is for example, you have 0, one is class level 1, another is class level 2. So there will be a perceptron. Okay, it will decide whether it is class level 0 or not. It is 0 or not. And then you will have another perceptron. This will also combine them, and it will decide whether it is 1 or it is 1 not. 1 not means it can be any other. Okay, so it is either 1 or it is not 1. And then you have another class. Okay, that's actually, it will say that, okay, so this is 2 or not 2. Okay, in this way you can do. So each perceptron can only do it with 2 class levels, 0 or not 0. Okay, so here if you have, for example, 3 class level, okay, so you see that for this neuron, this perceptron, you have this W1, W2, W3, W4, these 4 connections. Okay, so this will consider with the different weightage of this x1, x2, x3, x4. This neuron will consider with a different weightage. Okay, so for this for classification of 2. Okay, yes, fine. How do we decide the value of weights and bias? That we are going to discuss now. Okay, so that's actually learning. So we have this geometrical interpretation of this perceptron. We have these different examples, and now what we wanted to do, we have, for example, x1 and x2, and then we are actually making a y is equal to w1 x1. Sorry, it will be w1 x1 plus w2 x2 plus b. Okay, this is actually equation of line. Okay, so w1 x1 plus w2 x2 plus b. And then if you see that the visualization w1 x1, if you have this x1, it is x2, this is a L line. So this will decide where actually you are placing this line. Okay, so that will decide that, okay, so if this all these examples are in this one side, then it will be of one blue category, otherwise it is in the red category. Okay, this is the separator. If means when I go for this linear combination, that means w1 x1 plus w2 x2 plus b, it is actually meaning a line. Okay, in a 2-dimensional space. In 3-dimensional space, if we have 3 dimension x1, x2, x3, it will be a plane. If I am having n-dimensional space, it will be a hyperplane. So bias can be considered as another way to neuron. So for example, if I was explaining that if I'm having w1 x1 plus w2 x2, all this greater than equal to b, and then it is positive, and then what I did, I wanted to make this right side as 0. Okay, so then this right side for 0, I have written minus b into 1. Okay, so minus b greater than equal to 0, and this equation I can write using simple formula minus b into 1, where minus b I'm considering it's a weight and another input is 1. Okay, and then this x0. Okay, so if you have 3 inputs, then in these 3 input examples, you will have always the first example is 0, x0, and it is 1. Okay, so that we consider here. So you have now, so let us consider that you have this x1, x2 with this w1, x1 is coming with this w1 weightage, x2 is coming with the w2 weightage, and then we have the w1 x1 plus w2 x2 greater than equal to 0 or not. And what we are doing, instead of this w1 x1 plus w2 x2 plus we have w0 x0, where w0 I can say that it is a bias. Okay, it is simple bias, b into 1, that means it's a bias only. So this equation actually it is same. Okay, so I'm just rewriting. Okay, the style is different, but it is actually same. Here I had a bias term, and instead of this bias term, I'm just here you have this bias term b, and this bias term I am adding I am just rewriting using a simple another formula where I am considering that you have another input x0 that is +1 and which is added with the w0, and that is the b. Okay, where b is w0 and x0 equal to +1. So what is what is the benefit here? If I'm just writing in this way, what is the benefit? So benefit is that I can rewrite this full formula using a simple formula that wi xi I equal to 0 to n greater than equal to 0 or not. So I do not need to write any b term. So b is already included in this formula. Where b is included? Because if I just deduce, it will come as w0 x0 plus w1 x1 plus all those terms, and w0 x0 is 1 and w0 is b. Okay, and this you have these other terms. So it comes as this you can write in a simple way wix. Okay, so that's why I am saying that b term can be considered as a weight of a features that is 1. So you have some weights features, a height, width, and some others, and you have to consider some another feature that is 1. Okay, so let us consider now this our previous examples. Okay, we have this different data and this two-dimensional space x1 and x2, and this can be a possible solution. Okay, so if you have some data, positive, negative data, and I see that if I'm just making this w1 as 0.6 and w2 is minus 0.4 and b is minus 0.15, well, then this formula, this line becomes this one. Okay, so if I just set this w1 as 0.6, w2 as minus 0.4, b as minus 0.5, then this line becomes this. Okay, and then given a new example comes, this one, then I'll say that this example is in this right side, then it will be red. If examples are coming in this left side, this will be blue. Okay, now this, if once we have, this is a good combination for separation of this, for this application, for these points. But we used some other features, other point values. If you remember, in our problem, we said that w1 is 0.75, w2 is 0.25, and b is minus 0.5. But the actual solution is this one. So this will not, maybe if you just see this w1 0.25 minus w2 0.25, so this may come something like this. This may not be a solution, proper solution for this data. So how we can find these values, w1, w2, b, all this? Because we have to find out what is the best combination of w2 or w1, w2, w. Yes, what are the combination of, how this x1 is weight, what is the weight of x1, what is the weight of x2, and what is the bias? We cannot just find out randomly and see that, okay, whether it's working, because this is a good number. Okay, this combination. How we can get to this solution? How to find these values of W and P? Okay, that is the learning. So we have this learning that of W and B. This is perceptron learning. So what we do? How we will learn this W and B? So what we start? We start with randomly these weights. Okay, so when I say these weights, this means it includes the bias as well. Okay, so randomly we start these values of weights which is from 0 to 1 anything, and then that will be a model. And if that is a model, means that's actually a separate, a line, and that will tell me that, okay, so given some another example comes, I will say that, okay, so whether this example is in this right side or left side. Okay, if it is in the right side, then that means this it is my actual this is my prediction, and then actually there is also some downput. Okay, so I given some examples. So for example, I am having some examples like x1, x2, and you have some y. Okay, so with some examples like 0.3, 0.3, and you get plus level as well. So what we do, we start with some, for example, like W1 as 0 and W2 as 0. Okay, and then we just multiply and see that what, and W0 also we have to set. Okay, W0 for example, it is also 0. And we see that whether this value with this W10, W20 and W2, W0, W1, W2 all are 0. If we just multiply with these weights, with these features, and what will be the prediction? Whether this total sum is positive or negative. The total sum is positive, that means the outcome is positive. That means it is correct. My weight values, whatever I have said, these are correct. Okay. So this is consider this input from the training data and compute the outputs. Okay, why? So means whatever my prediction. Okay, so based on this weights, what is my prediction? If this prediction is same as the actual output, means already it was given. Okay, so this was given in the true training data. If both are correct, if we just compare this actual value and this predicted value. If both are correct, then we do not need to change anything. If it is correct, if it is not correct, that means I am not getting good result. There are some errors. Then I have to adjust the weights. So adjust the weights means I have to modify those values of these W's. So how we will modify that I am going to discuss. Okay. So I have to change these weights. So I will start from W1, W2, W0 with some numbers, W1, W2, W0 with some numbers, 0, 0, 0, and then I will change these values. Okay, slowly, and see that with which combination this data actually works. Now let us see that with some examples that how we can adjust this weight. What is the formula? So the formula of adjusting this weight is very simple. So you will be modifying these weights. Okay, so with this simple formula, Wj is equal to Wj means if you just consider, do not need to consider j, W plus W is equal to, you have this old value and this is the new value. Okay, so you are changing this old value with some modification. So if I have some value like W1 was 0, I am changing for them W10 to 0.5. Okay, so some numbers I am changing, means whatever I had. So if my W1 was initially 0.5, I'm changing from 0. It's like tuning. Okay, so 0.5 to I can modify to 0.45 or I can modify to 0.55. Okay, so something whatever I had this previous value, so I'm just changing plus minus. Okay, so that's what I'm doing. So I had some old value and I'm changing with this value like eta into d minus y into xj. D is the ground truth or the actual value and y is the predicted value and xj is the feature. Okay, so that's it. So I am just multiplying this d minus y into xj into some scaling factor. So whatever the multiplication comes, I'll just multiply with, for example, 20% or 30% of this value, and then I will modify. Okay, so this that's the principle of this weight modification, and let us see that how actually it works. So given a example, okay, so this is the formula of weight modification that I have already discussed in the last slide. So dr minus yr is, if you have d is the actual ground truth and y is the predicted output. If d minus y, okay, if it is same, means whatever actual and whatever you are predicting both are same, that means you do not need to change anything. Okay, that means the difference is same. Okay, so it is 0. So you predict 0, it is also actually it is 0. So that means it is difference is 0. If it is 0, then whatever you do, the multiplication will be always 0. That means there will be no change. If d is 1, okay, the ground truth is 1 and actually you are predicting 0, so you will be adding with some positive value, okay, plus 1. Means it will be plus 1, okay, plus 1 into x means features and scaling factor. If d is 0, y is my 1, that means you are adding, means subtracting this value. So that's why as I was saying, if it was 0.5, either I will go to 0.55 or I will go to 0.45. So based on this change, that if this dr minus y is, if d is actually 1 and you are predicting wrong, that means I will be, I am doing something mistake. So I will be adding, okay, 0.5 to I will go to 0.55. If I am doing something as d was 0 and I am predicting 1, then I have to reduce. Okay, so that's this is the simple calculation that I am changing these weights. So here I see this one example. W1 was 0.75 initially. So, and then X1 was 0.35. Okay, so let us consider this one. W1 was 0.75. This is the weight. Okay, so these features are all multiplied with this 75%. Let us consider 0.75. And this is X1 is 0.35. And dr minus yr was minus 1. Okay, and eta is the scaling factor. So what will be the next value of weight? Weight will be, this is the old value, that is the 0.75 plus scaling factor 0.2 into d minus y. D minus y comes as minus 1. Okay, so minus 1 into 0.735. So I have just multiplied this and then it comes 0.67. So first time this W comes as 0.75, next time it is 0.67. And then again you have to check that whether what is the predictions. Okay, and then accordingly we will be modified. So this is the way we are doing this modification. Now let us see one examples. Okay, so how actually we can modify this all these weights. Now it will be clear. So let us consider now we have two features, x1 and x2. Okay, and then these are the data, four data, 0.01 minus 0.3, 0.2 minus 0.4, 0.4, 0.8, 0.7, and these are the ground truths. Okay, 0, 0, 1. Okay, these are the four different features like height and width, and this is the outcome. And what we are doing, we have two weights, W1, W2. W1 will be multiplied with X1, W2 will be multiplied with X2, and we have W0, which is which will be multiplied with X0. X0, that's actually W0, X0, it is coming as B bias. Okay, so we have this these three weights, W0, W1, W2, and X0 will be always 1. Okay, so because it is just multiplied with this W0. Now I start with some random value. Let us consider this random value is 0.1, 0.5, 0.4. And eta is the scaling factor. We say that it is always 0.3. Now what we do first, I'll be multiplying these features with these weights. So what will happen? X0 into W0. So this is the way. So I am doing this X0 into W0 plus X1 into W1 plus X2 into W2. If I multiply, this total comes minus. That means the outcome will be negative, 0. Okay, if it is greater than or equal to 0, it will be 1, otherwise it will be 0. So my prediction is 0. And ground truth is also 0. So that means I am correct. Okay, so with whatever weights I have taken, I am correct. That means there is no error. Perfect. So now let us go to the second example. So with the second examples come, so W0 I'll be modifying again. Okay, so sorry, not this one. So I am doing this all these examples for the second example, third examples, fourth examples. I'll be doing all these multiplications and say that whether it is correct or not. And how I'll do it. So I first, with this first step, I didn't modify because as my ground truth is correct, I do not need to change these weights. Okay, so that means my weights will be same. My weights are remaining same. W1 was 0.5, so it is W0 is 0.5 and 0.5, 0.4. These are remaining same. Now I'm just multiplying with this X0, X1, X2. So if we see that if we multiply, this comes as 0.36 and it is positive. So this my prediction is 1. Whereas my ground truth is 0. That means this is wrong. So what to do? There is an error. Okay, 0 minus 1 means minus 1. So I need to change. So the value of weights will not to be changed. How? Wj, all these weights will be changed to Wj, whatever old value plus scaling factor into d minus y into xj. So we have these three W's. So W0 was 0.1, 0.5 and 0.4, right? So these things we need to modify. 0.51 plus 0.3, d minus y was minus 1 into x0. Okay, so it was W0. So it will be 1. It is 1. X1 is 0.2. Okay, and x2 is 0. So if you just multiply, you see that these are the new values of this W0, W1, W2. So the next step, my W0, W1, W2 will be this one. This is the combination. And I have to do it again. So with this combination of this W0, W1, W2, if I multiply this X0, X1, X2, and see that what will be the outcome. Okay, and here I see that my prediction is 1, ground truth is 1, that means there is no error, correct? Then I am doing this for the fourth example, there is no error, it's correct. Okay, so I'll be doing again and again. So I have to repeat, okay, this process again and again. At some point, I'll see that weights are set in such a way. Okay, you see that in this example, here this weights will be set minus 0.2, 0.44, 0.28. And all these outcomes, predicted outcomes, and this ground truths, these are all same. 0, 0, 0, 0, 1, 1, 1, 1. Then I have to stop. I do not need to change the weights. This means this combination of this W0, W1, W2 is set for this example. So given any new data, okay, so let us consider that you have another example like 0.8, 0.5. What you will do? You will be predicting. So given a new example, you will be predicting with a 0.8 into 0.44 plus 0.5 into 0.28 plus W0 into X0 means 1 into minus 0.2. Whatever it comes, if it is positive, then it will be of 1. If it is negative, it is 0. Okay, this is the predictions. Okay, so given a new examples, I predict like this. So these weights, whatever I set using this training, that's actually the final weight combination. So based on this weight combination, given a new data, I can predict, okay, just I will multiply with this x1, x2, x3 and get the results. That's it. So what I am doing in this visualization, if you see, I have start with some random samples of W1, W0, W1, W2, and then slowly it will be modified, and at some point it will set that, okay, all these examples are correct. And then given a new example, okay, so you just fix it, okay, so it is correct or not, and then you will get the answer. Is it okay? So yeah, now we can take some questions if you have.
Yeah, so there are a couple of questions. I am going back. So why and how we are setting the probability of different, for example, something she has written, probability of different weights. That is not very clear what she means. So probabilities of probability different. And there is another question, for each instance, the same process is repeated for weight adjustment. And the third question is, if output, so should I tell the questions one by one or?
Yes, one by one will be better.
Okay, fine. So the why and how are we setting the probability of different?
There is no probability here.
Yeah.
We do not have any probability, right? We are just doing this weights, weighted summations, that's it. So we set with some initial randomly weights. For example, we have, I repeat here, what we did, we have x1, x2, x3. Let's consider these three features. What we are doing, we are just multiplying with with their weights, w1, w2, w3. Okay, so these weights we just multiply. That means x1, w1 plus x2, w2 plus x3, w3. Okay, we do this multiplication, and there we have a bias term comes, and then what it says that whatever outcome it is, and then we decide whether it is greater than equal to 0 or not. So if this total value is greater than equal to 0, then it is positive, otherwise negative. There is no probability term. Okay, so these are all weights. So weights are multiplied with these features. And then how these weights, actually these are set with some random values. 0, you can set with anything. For example, with this, you have these three W's, W1, W2, W3, and B can consider as W0. So I set as, so you can set also 0.5. Okay, any values. You can set any values. And then we see this for any example. Some examples we have to fix. Okay, that I already shown. That for one examples I take, and then we just check with this multiplication or these predictions whether it is correct or not. how I'm doing this prediction? Just I'm multiplying x0 into w0 plus x1 into w1 plus x3 into w3. Whether this total sum is positive or negative. If this total sum is positive, that means it is 1, otherwise it is negative 0. So that's it. This is the prediction. And this prediction, if it is correct, then I do not need to change the weights. If it is wrong, then I need to change the weights. So if it is wrong, I need to change the weights. Then what is the rule? So that's the rule, simple rule. So whatever old value you have, for example, if you have this W0 0.5, so, and then I'll be modifying with this scaling factor into features, values, and then d minus y. Okay, d minus y is the, you see this is either 0 or plus 1 or minus 1. Now this modification will be done for all the weights. Okay, so if we get one error, then all these weights will be modified. So you see that in the first step, I didn't get any error. That means there is no change. In the second sample, I got error. So all this W0, W1, W2 need to be modified. Okay, W0 is modified, W1 is modified, W2 is modified. Okay, and then if we see this with this next new W's, I will check with this third example. If it is correct, I do not need to modify. If it is wrong, then I need to modify again W0, W1, W2, all this. Okay, these weights need to be modified if they are wrong. Otherwise, if this is correct, there is no need of changing. Yes, yes, madam.
The second question is, for each instance, the same process of weight adjustment is repeated.
Yes.
Yeah. Another question so this was by Satya Devi, Jyotsna is asking, if actual outputs are not available, how can we adjust weights?
No. See, you have this training data. So when you are doing some supervised machine learning, right? When you have seen already this given some data. Okay, so you have data x1, x2. Okay. And then you have several examples, 1, 2, 300 examples, let us consider. And then if you do not have labels, that means it will come as a unsupervised machine learning. So you do not have any labels. Okay, that means all these examples are of same level. So you cannot do anything, classification. If you have labels, that means some labels you have some y. That means either 0 or 1. Some labels are there. That means you can make some classification. Now you have some label that, okay, some of these examples are blue, some of these examples are green. Okay, so then based on that, you can actually say that, okay, this prediction is either 0 or it is red or blue. You should have, in supervised machine learning, this target 0, 1, these labels should be there. That is the difference with this unsupervised machine learning. In unsupervised, you do not have this level. This column outcome target is not there. In supervised, it is there. So when we say that supervised, that means this red and green, this coloring will be there. And then accordingly, we can say the prediction that whether our prediction is correct or wrong. Yes, madam.
So next question is by Josephine. She's asking, if the weights are set and the prediction is equal to actual output, the error should be 0.
Yes.
Yeah, slide number 28 she is referring to.
28.
Yeah, that is clear. Like.
Yeah, so because I think it is the previous step. Okay, so how actually we modified this weight. After this modification, this is the result.
Okay. And then how we make learning rate, how we take learning rate, and how to decide the initial values of weight. Is there
you see that here, just to continue that, here it is the W0 is minus 0.2, 0.44, 0.28. Okay, you see here 0.2, 0.44, 0.28. Okay, so these values are learned before this step. Okay, so once we have this, just I didn't continue all these steps. Just I have shown you these 2 steps and last step. And once we have this last, okay, so this, for example, if we have this these features, and there, if some another example is coming and it's an error, then I need to modify with these values. Okay. So W0, if another example is coming with error, then I need to modify this. Okay, W0 will be some other values. Instead of 0, okay, it was minus 0.2, it will be 0, 0 point, minus 0.2, 0.44. If there are some error, otherwise I do not need to do anything. Yes.
So some people are praising that. Very good explanation. It's crystal clear. What is the role of learning rate is another question.
Yes.
And how it is different than batch learning?
Yes, batch learning will be covering tomorrow. Okay, so when we will have this optimizations, tuning, that we will be discussing. So that time we will be covering this batch learning. So, but I wanted to discuss this learning rate. Yeah. So learning rate I wanted to cover in this multi-layer perceptron, but it is okay. So this multi-layer, this scaling, what I said, this eta. Okay, so this eta is actually the scaling factor, or you can say that learning rate. So for example, when we have this learning rate is like, for example, whatever we are getting, this total sum, okay, like total sum, for example, if you do not have this learning rate, like this, here you have this learning rate. What was the learning rate here? 0.3. Okay, so this 0.3, if it is not there, then what will happen? So then this addition, okay, this, for example, whatever I am just multiplying, this will be huge. So instead of this 0, if I want to have 0.5, and next time change will be 0.9, or it can be 0.1. Okay, so means my tuning will not be good. So what I'm doing, I want to change very slowly. So I want to move, okay, so 0.5 to 0.51 or 0.52. Okay, so very slowly I want to change this weight so that I can get to the minimum error. Means all these examples are correct. So if it happens that if I'm not doing this with this, if I'm not doing with this scaling factor with very small, then what will happen that if you have this error surface, okay, this is an error surface, like if you just considering this single weight, okay, this weight, okay, this for example, you have this x1 and I'm just considering this weight w. So for w1, these values can be 0 to, for example, 1, okay, and then I start with some random value like 0.2, and then what, and this is the error. This error means y-axis is error means if I consider w1 as 0, then what is my error? If I'm considering 0.4, what is my error? Okay, so this is the error surface, error curve. In y-axis it is error, and this x-axis it is the w value. Now this curve looks like this. Okay, so and you see that this is the minimum. Okay, so I start with some 0.0 value, and then error is 0.2, and then if I modify, so it will be 0. This error is actually going down. Maybe it will be whatever error I have, it will be less. So if I'm just modifying from 0.5 to 0.7, so what will happen? 0.8. So I am just very close, and suddenly my weight will be very large, and then my error will be more. So instead of this 0.5253, if I'm just not going down slowly, okay, so if I'm just jumping with this weight value, which is 0.5 to 0.8 or 0.5 to 0.2, my error will be jumping like this. Okay, for example, 0.5. Okay, so here my error was this, and then I'm just changing to 0.8, my error will be like this, and then I'm going 0.2, and then my error will be. So I cannot actually converge. So this learning rate is actually, if you make it slow, that means the scaling, this reduction or the changing of these values of these W's will be very slow. Means I will tune this value slowly so that I can go to this error surface slowly, and I can converge to this minimum error. That's the way. That's why this is called learning rate. Means how you are learn these weights. Okay, so whether it will be fast or slow. So if you want to do it fast, then maybe you may miss the minimum error. So you may go with the slow one. Yes.
So the next question is, how do we record the outputs of, so this is by Professor Saeed, He's asking, how do we record the outputs of the network to check which outputs have matched the target? And how to choose the scaling factor value while updating the weights?
Yeah, I think this will be covered in the practical lessons, right?
Yes. So need to know, some Kaira is asking, need to know the rationale behind defining the learning rate.
Yeah, that I have already discussed.
Yeah, you have already discussed. Is it required that addition of all weights should be 1? Summation, perhaps he is saying, summation of all weights should be 1.
It's not required, not necessary.
Will this learning rate be different for all the weights?
Yes, of course, it's possible. No, learning rates for all these different weights. Yeah. Usually no. Okay, so you start from this beginning with all the weights with the same, I think, scaling rate. But it's possible that after some steps you can actually change the learning rate. You can go from the 0 slower to this more faster. Okay, and then you can do it. So maybe you can do it initially with 0.23, and then after that you increase the rate to 0.5 and 0.6, and then you can do it. Okay, these are possible. Okay, so maybe before you start with the faster process, and then you can go to this slower. Okay, so after different iterations, you can change this learning rate. This is possible, but for some examples, some learning rate, and for different examples there will be different learning rate. I think this is not possible. This cannot be done.
Yeah. So if the initial values, this is asked by Piyush is asking, if the initial values of weight are far away from what is supposed to get desired output, then it would take more steps to reach.
Yes.
And so how to decide the first value so that it hits the
there are several algorithms also for this, but if you are starting, just to start with 0 or 1, anything, there are several functions also, like some methodologies, methods like EF functions or some other seed functions, which actually starts with some initial values of these weights.
Yeah.
Okay, so there you will learn, I think, in this programming. Okay, this concepts. But whatever you have, so you will get to this minimum values.
Anish is asking, why does error function follow a parabolic shape?
Okay. So these are actually this. For example, if we are considering this error surface. Okay, so error surface, it will be something like this. Okay, this is actually, for example, it can be some different weights are there. Okay, this is, for example, if I'm just considering this W1. Okay, so there can be 2 different surface, 3 different. If I'm just considering one surface, and then you have this error. So it's not always that parabolic. Okay, so it's actually, it will be more on this, so something like this. Okay, some curves. So where there will be some local minima and global minima problem, that you have some surface, some error points will be there, which is a minimum, but this is not the best solution. And there are some points which is actually the best solutions. Okay, this convex problems. Okay, convex error surface you will have, and then you want to reach to the minimum surface, global minimum. This is the global point, and this is the local point. And then if you start from random points, so you may stuck in this local minimum. Okay, this is possible. So there are also solutions that how actually you can go from this, and then you can reach to this global. That we are going to cover next tomorrow. Okay, so there are different optimization functions are there, like for example RMS probe, atom. So this will take from the local minima to this global minima. Okay, so shall we continue, madam? We have this MLP part. Hello, are you there?
Yeah, so the number of, I'm sorry, I thought I was speaking, but I was muted. So Mr. Raja is asking, the number of neurons in the input layer depends on the number of input columns that we consider for features.
No. Here you have we just consider only one neuron, right? That's why it's a perceptron. whatever features you have, x1, x2, x3, x4, what we are doing. If you have 100 features, then also we are doing a single neuron only. So what we are doing, the single neuron is actually multiplying all these weights, x1, w1 plus x2, w2. So you have a single neuron for one output. Either it is sea bass or salmon. It is 0 or not 0, 1 or not 0. Okay, this will give you only 2 class problem. That's it. Whatever features you have. If you have 100 features, 1000 features, it doesn't matter. It will give you only one output.
And one last question. Yes, sorry.
Yes.
One last question, but Darshan, will you please say, I have unmuted you.
Hello, sir. Am I audible, sir?
Yes, yes, yes.
Sir, what is the role of that bias input, sir? What is the significance of that bias? What is the effect on the neural network, actually, that bias?
Okay. So bias actually, so as I explained, this bias, if you do not have bias, then this total sum, okay, so whatever total sum you will have, then you will have to check with some thresholds, right? So for example, this examples like length of fish, okay, I said this length of fish will be, for example, it is 0 and it is going to maximum 10. Okay, this fish examples. Some fish examples will come 3 lengths, some fish examples will come 5 lengths, some fish examples will come 8, 9, 7, something. So if you do not have any bias, so what you will say that I am just considering this whether the length is greater than equal to 0 or not. That's it. Bias will help you that L plus B greater than equal to 0 means B is 7. Okay, so I'll say that whether here B is equal to minus 7, L minus B greater than equal to 0 or not. So whatever length I am having, so if I just subtract 7, then this will come towards the origin, okay, towards the 0. Okay, I'm subtracting, so the length, whatever, for example, the length is of the fish is 9. Okay, so what I'm doing, so I am subtracting this 7. Okay, so bias is this 7. So I'm just subtracting this 7 from this 9. So that comes as positive. So if it is positive, then it is sea bass, otherwise it is salmon. If I'm not adding bias, then I have to use, okay, so I have to use this L plus B. Okay, so something like always I have to, so this bias is not there, so that means always it will be greater than equal to 0. So whatever examples you have to take that, okay, so fish length is greater than equal to 0, always positive. Then how can you decide all examples are positive? So this, there you cannot differentiate. Okay, so either it's a salmon or it is sea bass.
Sir, in that example, no, sir, you have mentioned that bias is equal to 1, right, sir?
No, bias is not 1. Bias, okay, so what I say,
Hi, sir.
This one, or in this, this which slide? Here.
This one, sir.
Yes, where bias is, you have this bias is B, okay, which is nothing but W0 X0.
Yes, sir.
Okay, W0 X0. Now, if you consider the W0 X0, X0 is 1.
So what happens if we initialize that X0 is equal to 0 negative value, then what will be the impact on the network, sir?
Okay, so B, if you change this X0 with some other value, then this term will be different. Okay, this multiplication, this X0 W0, this B is X0 W0. If you change it to, for example, 0,
okay, sir,
then B will be 0 only. So there is no bias.
Okay, sir. Thank you, sir.
If you add so 1, that's why this W0 is coming to the picture. That's W0 is the basically B. Okay, so X0 is just a simple unit multiplication. X0 is no value having. Okay, having no role in this multiplication. X0 is always considered 1. If you are considering B, W0, X0 as minus 1, then your calculation will be different. Then you have to, means it will also work. Okay, so if you consider this X0 instead of 0, instead of 1, instead of 1, you consider the x0 is minus 1. Then also it will work. Then this W0, if you finally you got 0. This final answer is 0.22, then maybe in this, if you consider minus 1, this final answer will be minus 0.2. Then minus 0.2 to minus 1, it will be plus. Okay, so means at the end, it will give you the final at the same solution. Okay, W0 x0 plus W1 x1 plus W2 x2, it will be greater than 0. Either you make it minus 1 or here, whatever you do. Okay, so finally it comes as W0 x0 plus W1 x1 plus W2 x2. Okay, so this is the total sum. So either you make x0 as plus 1 or minus 1. So accordingly, this W0 will also be different. Means it will start, for example, with some random value. Then this, if you change, okay, this multiplication, this modification, you will see that modifications, adjustment of this W will take you to this this negative value of whatever you receive with this positive. Yeah. So in this problem, for example, here, this you see this W0 comes as minus 0.2. If you consider all are minus 1, then maybe it will be plus 0.2. So at the end, it will be coming as B is equal to W0 x0, which will be minus 0.2 only. Okay, so is it okay? So we can continue. Madam, is it okay?
Yes, please continue. Now we have only 15 minutes, so you can. Yes.
So we have now learned this perceptron. So perceptron is a single unit which actually gives you this binary classifications for n number of features. And then drawback of this perceptron learning is that it can actually classify the data which are separable by a linear line. Either it is the data all are in this, for example, positive data are all in one side and negative data are in the other side. Okay, so all this, for example, AND problem, OR problem, NAND, these are of Boolean functions data. So for example, you have some data like this. So where you have this, if you consider this as the outcome, okay, Y target, okay, these are the input. So all the data outcomes are separable by a single line. Okay, so separate linear line. So OR, NAND, no. But the problem will happen with this XOR. Okay, so in XOR, we actually cannot solve this using a single perceptron. Okay, so this single perceptron will not help you for this solution. So how we can do it? So you see here, this in XOR problem, we have 0, 0, it is 0, outcome 0, 0, 1, 1, 1, 0, 1, and then 1, 1, 0. So we have some data, which is actually some positive data, for example, here, and some negative data here. How will you separate with a line? Is it possible? Can you do it? So you cannot do something like this or something like this. It's not possible. Okay, so you cannot do with a simple line. So single perceptron will not be able to solve these kinds of complex problem where the data are not separable by a single perceptron, okay, single line. So we require now help of multiple perceptrons where each perceptron will solve some part and then finally will combine their solutions together to get the final solution. So what we'll do, if you have these kinds of data, okay, so the objective will be, we have one separator, okay, one line which will solve, for example, this part, another solution, another separator which will solve this line, okay, and then finally both will be combined by another line, okay, and that will give you the answer. So there will be multiple perceptron will come together, and some perceptron will take some of this sub-problem to solve. Another perceptron will come to take, solve some other sub-problems. And then finally, another perceptron will come to combine their solutions, sub-solutions together to get the final solution. That's how actually this multiple perceptrons works. Okay, so if you have these two inputs, okay, so here you have in multiple perceptrons you have one new perceptron, another perceptron. This will solve a part. Okay, so this will solve, for example, x1 and not x2. This will solve x2 and not x1, and then this final one, it will combine. So this way, this for example, this three perceptrons. Here we have previously we had only one perceptron. Now we are considering three perceptrons to solve this problem, because the problem is complex. So that's actually leads to our next level, that is multi-layer perceptrons. Okay, so where we have these features like, for example, age, W, and density, some features, and then you have some perceptrons. Okay, several perceptrons, P1, P2, P3. Okay, some perceptrons which are all doing the same thing. Okay, and then these perceptrons, this perceptron is doing some solution. This perceptron is some, and then there will be some another perceptron P3, which is actually combining this P1, P2 together. Okay, and then P1's data and P2 data. This is also a perceptron. Okay, so that is also means whatever data you have, that will also combine by a weighted sum. Okay, and then it will make this summation, and then it will make the functions. Okay, so like neural network, biological neurons, a neural network we have seen, that we have one neuron which takes the data and then it processes and it provides the output to the next neuron. So, and then the next neuron also takes the data from the previous neurons and it processes and it provides to the next neuron. So same thing here. You have this multiple multi-layer perceptrons. Here we have layers of first layer, second layer, third layer, multiple layers. In first layer we have this several perceptrons which solve some parts, and these solutions come to the next layer, and these perceptrons also solve some other parts, and then finally there will be another guy perceptron which will take all these perceptrons data and it will solve. Okay, that's actually multi-layer perceptrons. It's called also feed-forward neural network. Okay, so it is taking the data. Okay, for example, you have a new data comes, it will the same thing, same perceptron principles. You make some weighted combinations, and then you have some functions which will provide the output to the next neurons. So whatever output you get from this each perceptron, this will be combined now with these weights, and then here also you will apply some functions and it will give you the results. Okay, so at the end you will be combining all these perceptrons data with this simple weighted combination W1, W2, W3, W. Everywhere you have these W's. Okay, so this will be combining, and at the end you are getting this final results. Okay, that's actually feed-forward neural network. So in this multi-layer perceptrons, in this CNN, okay, this convolution neural network, this actually follows in this simple principles. There is neurons are connected like this. There you notice that there is no connections from this future layers to this previous layer. These are all from this left to right. Okay, there is no. These are actually possible in this biological neuron, and this is also possible in this recurrent neural network. Okay, these kinds of architectures where we are considering this time series data analysis. Okay, so there we will have some connections which actually come from this output to this previous node. But when we go for this simple CNN based architectures, this kind of connections are not there. So that means whatever data are there, so this will be all propagated to the next layers. So we have these input layers, we have hidden layers and second hidden layers, and then output. So hidden layers, you have these input layers, we have these different weights, W1, W2, all this. And this each hidden layers, you have this different hidden layer 1, hidden layer 2. So you have this different weights. This will be actually multiplied, and then you get the results, and these results are multiplied again with another W2, and then you get the results, and that results are multiplied with these weights. Okay, that's how actually this, after each and layers, the same thing process, okay, are done. Now this is very important here. This in perceptron, we had to get one step function or threshold functions which provides the prediction whether it is category A or category B, whether if it is positive or negative. Okay, in multi-layer perceptrons, we do not do it in the beginning. So what we do, we use some other functions. Okay, so these functions are different, and these are called activation functions. In perceptron also, that's a step function is called activation functions. Okay, so which is actually not used in this multi-layer perceptron, because the principle, working principle in this multiplayer perceptron, there we need to use some gradient descent algorithms. Okay, we need to find some gradient informations, mathematical gradient information. That is not possible in this step function. So that's why the step function is not used in the multi-layer perceptrons. So what we can use? So we can use some other similar functions. Okay, instead of the step functions, we can use sigmoid functions. We can use this tanh functions, ReLU functions, other functions. So these are all same. So this what we are doing. So basically this the job is same. So whatever input you have, you just make the multiplication W1 x1 plus W2 x2, and then whatever you get the results. So this results will be produced to an output level. Okay, so which is from in sigmoid case, it will be from always from 0 to 1. So for example, if you have this perceptrons, okay, so perceptrons, we have this W1 x1 plus W2 x2. Okay, so just simple case. So whatever W1, the summations comes, okay, W0 x0. So if this total 0, it can come minus infinity to plus infinity, right? These numbers can come to any level. So then in this, if I'm just using this step functions, this outcome will be either 0 or 1 in the step function. In sigmoid also does the same thing, but it is doing in a functions, in a simple functions. It's a logistic functions. So here the function is sigma x 1 by 1 plus e to the power minus a. It will produce the results of 0 to 1 only. 0 to 1. This is the outcome. So whatever you have this range minus infinity to infinity, this range is from minus infinity to infinity x. Okay, if it is x, okay, so any value. So the outcome will be always from 0 to 1. Okay, so that's the range. So I'm just squeezing the outcome to whatever information you are having, I'm squeezing to 0 to 1. Okay, so that's the sigmoid functions work. So that's very simple. So this is the sigma x equal to 1 by 1 plus e to the power minus x. So that's whatever information you have, just you feed it there, and then whatever outcome you get in this from 0 to 1, so that is the result. Okay, so that is the value it will be producing to the next perceptron. So if you see in this figure, so what I'm saying that you have this W1, W2, and this guy, what it will do, W1 x1 plus W2 x2 plus B. Okay, and then here I am doing this sigmoid function. Okay, it is a sigmoid function, and this data, this range will be from 0 to 1. So means I'm squeezing this minus infinity to plus infinity to 0, 1. So the output will be from 0 to 1. So that's the output, and that will be multiplied with some another weights W3, W4, W5, and then I'll be doing some other sigmoid functions or something. Okay. These are the activation functions through which actually I'm squeezing this input, this summations to some other outcome. So we have the sigmoid, then tanh. Tanh also does the same thing. Okay, so these are popular activation functions which squeeze the input data, the summation data, to some simple limited range. Sigmoid did it in 0 to 1. Tanh using this equation, this formula, it does it from minus 1 to 1. And then you have this ReLU, this rectified linear unit. It is also doing the same thing. The output is 0, and here it is the range is positive. Okay, so if the x is positive, then y will be positive. Okay, but if x is negative, outcome will be 0. Okay, so if x is greater than or equal to 0, it will be x. If it is less than 0, it will be negative. And you have some other functions also, leaky ReLU. Okay, so there also it is similar to your ReLU. So if x is greater than or equal to 0, so it is similar like a ReLU, and if it is negative, then it comes as for example 0.01x. Okay, so 0.01x means, so if whatever negative value it is, 0.01 into multiplication ax. Okay, so that's the leaky value. So we have this activation functions, and now we see that how this using this activation functions we can make this training. Okay, so here we have lots of neurons, right? If you see one thing, just let me. We do not have time here. Just let me discuss. Okay, so for example, here if I am just saying that if I have a multi-layer perceptrons where we have 3 units, okay, 3 units means 3 features, okay, and in the hidden layer, first layers, I am having 5 perceptrons, okay, and then output is 2 neurons. Okay, so how many weights and bias are there? So this bias, this parameters, when I'm talking about parameter is equal to weight plus bias. So how many weights and bias are there in this architecture? If I use 1, 2, 3, 4, 5 and 6, 7 perceptrons. So you see that for this perceptron, okay, so how many weights will be there? 1, 2, 3. Okay, 3 weights and 1 bias. Okay, so this guy is also having 1 bias. This guy is having 1 bias. This guy 1 bias. Okay, each of them is having bias, and output is also having bias. So total number of weights will have 3 into 5 plus 5 into 2, okay, plus bias. You have this 1, 2, 3, 4, 5 plus 1, 2. So that means total 32. So you will have 32 weights, W1 to W32. So this many weights are there, we need to adjust. So as we have seen in this perceptron learning, how to adjust these weights. In this architecture, we need to adjust 32 weights. If my architecture is something like this, you have these inputs, hidden layer, first hidden layer, second hidden layer, third layers, and then output. Okay, so you see that how many weights will be there? 100 units, 50 units, 50 into 100. Okay, 50 into 100, then 100 into 1 plus 1 into 100 plus 100 into 50. Okay, and then you have this bias. You have this 100 plus 1 plus 100 plus 50. So if you consider, there will be 10,451 weights. Okay, this many weights are there in this architecture. So you have this different multi-layer perceptron with this according to this different neurons in different layers. So it's actually up to you how will you design, how many layers of neurons and how many neurons will be there in each hidden layer. So you see that here I am considering 3 units. Maybe that the same principles you do not need to have 1 neurons. Same applications I can have multiple architectures, and maybe this architecture produces accuracy of 78%. In this architecture I can get 87% accuracy, but you will have this many data, this many weights. Okay, so we need to fit all this, we need to find out the values of all these weights, how we can do it. So that's actually we have to learn this multi-layer perceptron learning. So this learning can be done using this back propagations. Okay, so back propagations, we have this algorithm. It is specially for this multi-layer perceptrons. Okay, so if we do not have these parts, let us consider. Okay, so we know if we have this only these parts, then we know that it is simple to perceptron. We know how to train it, but how to train this internal weights? If these weights are there, I can know. Okay, using this perceptron learning, I can adjust. But what happened with here? How can we adjust? Okay, because these are internal. So this process will be done using this back propagation where there are two steps. One is forward step, another is backward step. Forward step, what we'll have, so we'll be setting with some simple weights like we did last time, W1 to W32 or something randomly. Okay, so initially we set all these values with some random number, and then whatever values we have, these features, okay, x equal to, for example, 0.3, y as 0.5, and z as 0.7, okay, and then we just multiply, and we have some activation functions. So activation functions, let us consider that we are considering the sigmoid activation function. So we'll multiply them, and we get the results. We apply the sigmoid functions and get the output, and then we have these weights. We know multiplications. We have the sigmoid functions. We know this what is the output. So this is the forward step. Okay, just simply multiplications with these weights and using these activation functions, we can go to this outcome. And there will be a backward process, which actually, if there is some error, then according to this error, these weights will be adjusted. So this weights adjustment will be done from this backward process. First, I'll be modifying these kinds of weights, these weights. Second, I'll be modifying in this layer. Third, I'll be modifying this. So the process is in this way. So first, I'll be changing the weights of this, okay, from output layer to this last neuron layers, hidden layer. Then I'll be modifying these weights in this layer. Then I'll be modifying. So this is the backward step. First, I'll be changing here, second here, third here. That's how we'll be doing this forward layer, backward layer, and third, this first layer. So this training part, I will be covering tomorrow. Okay, so we do not have time, so I'll take tomorrow. But I'm not going into details, just simple calculations. There are some mathematical details are there. I will not explain in details. But we will cover tomorrow. Okay, so we'll quickly do it. Yes.
So people are asking, please share the slides, sir.
Yes. Of course.
What is the need of activation function, and when to use sigmoid, when to use ReLU? And
okay, so these are some actually this for example, sigmoid, tanh, ReLU. These you have to check with these different applications that which one is working better. So for example, given a new data set, so you first check with this sigmoid, what is the results? You check with this tanh, what is the function, what is the results? Means whichever parameters, whichever activation functions you get the best results, that you will be using. Okay, so that's the usual process. These are all hyperparameters. But now people are all using, and they know because we have tested with these different parameters, and we have seen that ReLU is actually giving most of the cases better result. So if you do not have any idea that which one to test, so either you can compare all these different activation functions, okay, and then see that what is the results you are getting, and then take the best one. Otherwise, if you do not have time, you will just do it using ReLU and you will get the results.
so Mukesh is asking whether sigmoid or tanh is more prone to vanishing gradient problem.
That we are going to discuss, because we have not talked about vanishing gradient, right? Anyway.
While Anish is asking, while adjusting the weights using back propagation, is the weight adjustment happening layer by layer? Shouldn't it be all layers simultaneously?
No, it is not all layers simultaneously. It will be layer by layer, because we will first see here what we are doing in this perceptrons. We change the weights. Okay, so if we so if we need to modify all these weights, okay, so because you see this multiplications, this feed forward step, whatever weight is there, this is actually multiplied with the data here, and then it comes here, okay, output, and this outcome is multiplied with this weight, and it is multiplied. So these weights are not same, weights are different. So I cannot just change this weights in the same fashion. So there, of course, there will be some influence of these weights to this weight, that we are going to check that how this weights, whatever I am just adjusting this last layer weights, how it is contributing to this weight modification of this layer. Okay, so because this will be more contributing here, this will be contributing here. So we cannot change all together. If we change everything, then all will be simultaneous together. So finally, at the end, there will be chaos. Okay, we will not get any good solutions. So if we are doing it systematically. First we do here, and then we here, and then slowly we are changing.
So there is one more question that, like, if X and Y are two features to discriminate between two classes, what is the minimum number of neuron layers to design the neural network?
Sorry, can you, madam, please
No, actually, question is not very clearly written here. Murukesh ji, will you please, like, if X and Y are two features to discriminate between two classes, what will be the minimum number of neurons required? Like,
if the data are classifiable by a linear line, then a single perceptron is enough. If your data is, for example, like this, okay, then a single perceptron is enough. If the data is something like that, then it is difficult to classify with a single line, because how can you?
Yeah. So I don't think there are any further questions. It is always so pleasant, and I enjoy listening to your lectures, and I am sure that participants are also finding it so useful. They are writing. Thank you, sir. Thank you. Many compliments are coming up. So we, on behalf of, superb session. We agree with you, Anish. And so on behalf of Electronics and ICT Academies at IIT Roorkee, MNIT Jaipur, NIT Patna, NIT Warangal, and IIIT DM Jabalpur, I sincerely thank you, Dr. Partha, and to your lecture. Thank you so very much once again.
Recording stopped.
We will be meeting